Hello, and welcome to our first video covering topics in section 1.3 of your textbook. In this video, we'll start out by just slogging through some terminology, and then we'll take a look at some big theorems that talk about the relationship between the reduced row echelon form of a matrix, the rank of a matrix, and the solutions of the corresponding linear system. All right, let's dig right in. The first thing we're going to talk about is what it means to say a linear system is consistent versus inconsistent. Now, why your book waited until section 1.3 to define these terms is beyond me, because 100% they use these terms in section 1.1. But okay. First, a system with no solutions is called inconsistent. So that's just what it means. It can't be solved. And then on the other hand, a system with at least one solution is called consistent. So no solutions, inconsistent, at least one, consistent. And of course, we have to say at least one because, as we've seen, you could have like a bajillion solutions. So there we go. Next thing I want to talk about is leading versus free variable. And so you may have seen the term free variable when looking at parameterized systems of equations or something in the past, but here let's just be sure and define them in the linear algebra sense. So if a coefficient matrix, not the whole augmented matrix, but just the coefficient matrix, if it's in reduced row echelon form, then a column with a leading one will correspond to a leading variable, and a column without a leading one corresponds to a free variable. And so let's take some coefficient matrix, or I guess this is the augmented matrix, and then we've got the coefficient matrix here. Now, each column corresponds to a variable. So we've got our variable x, y, and z in each column. Those are the coefficients. And so if we're just blindly applying the definition, then a column with a leading one is a leading variable, corresponds to a leading variable. So, all right, a leading one is the first non-zero term in a matrix of reduced row echelon form, and it'll always be a 1. So, okay, this row, here's our leading 1. So this column corresponds to a free variable, leading variable. Row 2, the first non-zero entry here, this leading 1 is in the third column, so z is a leading variable. And then this column here, no leading 1s, so y corresponds to a free variable. So, okay, that's just applying the definition, but what's going on here? Like, let's translate this back into, Here, let's read what I said on the slide first. Yes, a free variable is so called because when writing the solution, that variable is free to be anything. So yeah, let's write the solution like we did in the last video. So translating this matrix back into equation form and then solving for the leading variables, we have x is minus 2y plus 3 and z equals 4. And then the solution in parametric form is going to be x equals minus 2t, y equals t, z equals 4. And so these, as I said, these free variables, so y, the free variable, becomes a parameter. And then each new value of the parameter, that parameter can be anything it wants to be, any real number. Okay, and the reason this is important to think about is that these concepts are useful for understanding the nature of solutions to a linear system. Because, all right, yeah, we have this free variable y, that becomes a parameter t, and suddenly any new variable of our parameter becomes a new solution. And so if you have a parameter, if you have a free variable, you automatically have an infinite number of solutions. If there are any, they're an infinite number. So that's why we introduce this terminology. It helps us understand the nature of solutions to systems. All right, another piece of terminology your book introduces is the concept of the rank of a matrix. So, all right, the rank of a matrix, by definition, is the number of leading ones in its reduced row echelon form. And, all right, that's just a lazy way of writing the reduced row echelon form of matrix A. Okay, so let's look at an example. Take some random matrix A. All right, this is not so random, right? It's just got 1, 2, 3, 4, 5, 6, 7, 8, 9. But okay, take our random matrix. And then we can't just say what the rank of the matrix is yet. We have to refify it first. The reduced row echelon form of our matrix A looks like this. And now the rank of the matrix is the number of leading ones. So let's count the number of leading ones. There are 2 of them. And so rank of the matrix A is 2. All right. Not too crazy, too difficult to apply the definition. But as we will see, again, this concept, we introduce terminology when it's a useful concept. This is the notion of the rank of a matrix is going to be helpful for understanding the nature of solutions. All right, so let's look at the theorems that unite the reduced row echelon form of a matrix, the rank of a matrix, and the solutions of the corresponding system of equations. All right, well, first, let's just let me tell you something that I don't know. I can't remember if and when your book actually says this, so I'm going to say it now. The reduced row echelon form of a matrix is unique. So that means if you are applying your Gauss-Jordan elimination algorithm, there's only one place to stop, and that is the reduced row echelon form. It's not like, oh, you get one reduced row echelon form, but if you kept going, you'd get another reduced row echelon form. No, there is only one. There's only one place to stop. There's only one way for the matrix to end up if you do the Gauss-Jordan to its completion. Okay, the proof of this fact involves a technique called mathematical induction. It's a proof technique that most books assume you haven't seen at this point in your mathematical career, and for this reason, your book does not prove it. Also, the proof is boring. Like, I can just confirm that, having read a few of them, and having been tempted to include it. I was like, okay, I get why they don't do it. But I mention it because the fact that this is true should give you some comfort, especially regarding what we're about to do, because we're going to talk a lot about what the reduced row echelon form of a matrix, like how it looks and how that corresponds to solutions. And that would be, it'd be real pain if actually there were multiple ways of writing the reduced row echelon form and then you had to be worried. So this is all to say, try to relax and just enjoy these theorems that are coming up. Okay, the first one we're going to talk about is Theorem 1.31 in your textbook, and I put quotes around it because your book doesn't prove it. Your book starts with some examples and was like, see? So I'm going to try to provide a little bit more of a general discussion about this theorem than your book provides. But this theorem, what's it about? This is a theorem telling you, explaining a little bit about the relationship between RREF and solutions to a system. So, okay, the first thing this theorem says is that a linear system is inconsistent, so no solutions, if and only if the reduced row echelon form of its augmented matrix contains this row, a row of zeros, and then a 1 to the right of the equal sign. So, okay. No solutions corresponds to RREF that looks like this. So let's see why this is true. Well, first off, there are 2 if statements here. If it's inconsistent, it contains this row, and if it contains this row, it's inconsistent. So let's deal with both in turn. So let's start with the idea. If the reduced row echelon form contains that row, then why does it have to be inconsistent? Well, if we translate that row back into an equation, what equation is it? Well, we have zeros on all of our coefficients left of the equation and 1 on the right. So that row corresponds to the equation 0 equals 1. And nothing satisfies this equation. So no matter what your original system was, to satisfy that original system, you'd have to satisfy this equation. Nothing will do it. There are no solutions. All right, now let's go back the other way. Suppose the system is inconsistent. Then it must contain this row, a row of zeros and then a 1. Because why? Well, you might think this is a bit of a cop-out, but the reason is if we didn't have that row, then we could solve for all the leading variables and just write down a solution. Like, the only thing that prevents, when you're in RREF, the only thing that prevents you from writing out the solution is if there's something that can't be satisfied. But if that row's not there, then everything else can be satisfied. You just write down the solution immediately. Okay, so that's relationship between RREF and an inconsistent system. Now let's look at consistent systems. So if a linear system is consistent, so it has at least one solution, then it has either infinitely many solutions. We've seen this before. And the claim is that this happens if its reduced row echelon form has at least one free variable. And the idea here is that, okay, if it has a free variable, then that free variable becomes a parameter when you write out the solutions. And the value of the parameter each new value of the parameter corresponds to a distinct solution. And the parameters can run through the reals, so you have an infinite number of solutions. So that's the thinking there. Or it has one solution, exactly one solution. And this happens if all the variables in its reduced row echelon form are leading. And the idea here is that, well, okay, if all the variables are leading, then each variable, like if we translate our reduced row echelon form back into equations, we just get each variable equal to a number. And that is our exact solution. So there's only one. Okay, so hopefully this doesn't seem too wild to you. In fact, like geometrically, you might be able to convince yourself that you either have one or infinitely many solutions based on like intersections of lines and stuff. But there we go. It's written down. It's quote unquote proved. Okay. Let's get into this is like the meatiest equation or theorem that we're going to look at today, and it's the relationship between the rank of a matrix and the solutions. Just as a reminder, the rank is the number of leading ones in the reduced row echelon form. So this theorem, actually, your book breaks up into examples 3 and 4, but it really is a theorem. So it starts by saying, consider the n by m coefficient matrix A of a system of n equations and m unknowns. So first, convince yourself that a system with n equations and m unknowns really does have an n by m coefficient matrix. Like the number of equations, that should correspond to the number of rows, and the number of n unknowns should be the number of columns in the coefficient matrix. So yeah, make sure you believe that. And I'll just write like a general n by m matrix here. So the first thing in this theorem is that the rank of A is less than or equal to n. So that means the number of leading rows, the number of leading ones has to be less than or equal to the number of rows. And this is most certainly true. And the idea is, remember, a leading one is the first non-zero entry in the row of the reduced row echelon form. And so if it's the first one in the row, there's going to be at most one leading one per row. And so, okay, the number of leading ones just has to be less than or equal to the number of rows. But also, the number of leading row ones is going to be less than the number of columns, less than or equal to the number of columns. And the idea here is when you're putting something in reduced row echelon form, remember you have to clear the columns. And so if you have a leading one in a column, then everything else is going to be zero there. So you're not going to get more than one leading one in a column. So, okay, these first two are true just really by the definition of the reduced row echelon form. But okay, that's, I would say, not that interesting so far. Here we go, relationship to solutions. If the rank of a matrix is equal to the number of rows, then the system is consistent. The idea here is that, all right, well, if the reduced row echelon form of the augmented matrix, if it doesn't contain this row, the reduced row echelon form of the augmented matrix does not contain this row if the rank is equal to n, right? Because here, this would be a row with no leading ones in the coefficient matrix. And so if the rank is n, it can't contain this row. And if it doesn't contain this row, then it has to be consistent by that theorem 1.3.1. Okay, all right. So rank can tell us something. Rank of a coefficient matrix tells us something about whether the matrix is consistent. And all right, another relationship between rank and consistency. Here are rank and solutions. This is claiming that if the rank is less than the number of columns, then the system either has no solutions or infinitely many. So why is this true? Well, if the rank is less than the number of columns, this means we have a column with no leading ones, which means we have a free variable. And if we have a free variable and the solution and the system is consistent, then we have to have infinitely many solutions. But if we have a free variable and whoops, we still end up with a row like this row here, okay, then it's inconsistent. We have no solutions. But that's it. If rank A is less than number of columns, then we have a free variable. So we have either no solutions or infinitely many. And then the last element of this theorem is that if the rank equals the number of columns, then the system has either no solutions or exactly one. Okay, so let's think about why that is true. So if the rank equals the number of columns, then there are no free variables. And if there are no free variables, then we can't have infinitely many solutions. So there we go. This is the meaty stuff here, and we will use this we'll use this stuff a lot. So this will come up many times throughout the term. But we're not done. The last thing I want to talk about, a little cleanup theorem, is this theorem 1.3.4. So here, now suppose we have an n by n coefficient matrix. So we have n equations and n unknowns. The system has a unique solution if and only if. And now this is something we might really care about. Like, when do we have a unique solution? How can we tell just by looking at, a matrix? Well, the system has a unique solution if and only if its reduced row echelon form looks like that. It has ones on the diagonals and zeros everywhere else. So, unique solution if its coefficient matrix, reduced row echelon form, is diagonal with only ones on the diagonal. This means that we can know whether a system has a unique solution without even knowing the right-hand sides of the equations. This should be a little jaw-dropping. I mean, you would think if you needed to know whether a system of equations was consistent or not, like if it had a solution or if it had a unique solution, you would think that you might need to know what the constants were on the right side of the equations. And this is saying, no, you don't. So hopefully this is showing you a little bit of the power of the coefficient matrix by itself, why we're interested in that beyond just the whole augmented matrix. Yeah, so I find this somewhat surprising. Then last thing I want to say is that this matrix is the holy grail of matrices. This is the best one, absolutely every mathematician's favorite matrix. We are going to be seeing a lot more of this bad boy in the future. So it might not be your favorite matrix now, like maybe you'd like the zero matrix better or one with all ones better. But by the end of the semester, this will be your favorite also. All right, I think I've said enough. See you in the next video.